Okay, what I'd like to do is go through a phase change diagram problem, and I want to answer the question that you see on the right side of the screen. It says how much heat is required to go from minus 25 degrees C to 150 degrees C with 10 grams of ice. So how would I do that? Well, the first thing I need to recognize is that I'm starting, if I'm at minus 25, I am below the freezing point. So we're dealing with water. And of course, the freezing point or melting point of water is 0 degrees C. So I'll kind of represent that here. But I'm down here somewhere. I'm going to start at minus 25. And I want to take it up to 150, which is going to be somewhere here above the boiling point. And again, our boiling point, if I can represent this, is 100 degrees C, exactly. So what ends up happening, I'm going somewhere up here to 150.0 degrees C. So how do I do that? Well, the first thing you need to recognize is that as I go within a phase, I need to heat this up and determine the amount of heat required within each phase, here, here, and here. I'm going to use the formula Q is equal to M delta T, which represents T final minus T initial, times the specific heat, which is represented by C or Cp. That's what's going to allow me to figure out the energy changes required in those areas, A, C, and E. When I am within a phase change, when I'm doing this portion or this portion, I'm going to use this formula, Q is equal to mH. H being the enthalpy or heat of fusion for melting, or the enthalpy or heat of vaporization for my boiling process. Once I do each of those calculations, I simply add them up. So I'm going to do this, and actually let me represent these with different colors. I can do them in independent colors. I'll do this. I'll do this. I'll do this. I'm sorry, this is 4 here. And then I will do this, 5. So I will do them each individually in these different colors. And then at the end, I'm going to simply add them all together. So here, let me start here. Okay, so for area 1, I'm going to do Q is equal to M delta T Cp. My mass, we've said, is 10.0 grams. My delta T, I'm going from 0, or from minus 25 to 0. So what is 0 minus negative 25? Well, that delta T represents 25.0 degrees times the specific heat of ice. And the specific heat of ice, I've listed my specific heats and enthalpies or heats of vaporization and fusion over here. But the specific heat of solid ice is listed here as 2.092, and that is joules per gram degree C. So if I multiply 10 times 2.092 times 25, I end up with 523 joules. Now that should have 3 significant digits because of these things. Never round based on a constant that's given to you, so that's going to be good to the ones place. Now let me do step 2 in red. Now that I've melted my ice, I took my ice from minus 25 to the melting point. I've now gotten it to the melting point. Now I need to melt it. Okay, the formula for melting is Q is equal to mH. My M again is going to be 10.0 grams. And since I'm melting, I'm going to use the heat of fusion for ice, which is 334 joules per gram. So when I multiply those, obviously I'm going to get 3,340 joules of energy. Again, I'm allowed 3 digits. I'm not going to round based on the constant here. So this is good to the tens place. Now going to my next phase, 3, I'm going to heat the water. It's now melted. I took it from ice at negative 25. With 1, I took it to the melting point of 0. With 2, I melted it. Now in 3, I'm going to raise the water from 0 to 100. I have to get up to the boiling point. So that's Q is equal to M delta T Cp again. And again, my mass is 10.0 grams. My delta T, I'm going from 0 up to 100. So 100 minus 0 would give me 100. Times my specific heat of water, which is 4.184, and that is joules per gram degree C. And when you do all of that calculation, I got 4,184 joules, which makes sense. I'm taking basically, this is 1,000 times 4.184, so you get 4,184. For my next section, okay, that's this area up here. I've now heated the ice to the melting point. I've now melted it, and now I've gone up 3. I've gotten it to the boiling point. Now I need to boil it, so that's going to be step 4 here. Phase changes, or Q is equal to mH. My M, again, is 10.0 grams. Oh, and by the way, the specific digits on this guy here, this would be good the 3rd place over, so that'd be good to the 3rd place there. And I'm going to use the heat of vaporization, which you'll see is very large compared to the heat of fusion. It's a much, much larger number. And again, that comes out, excuse me, to 2,259 joules per gram. 2,259 joules per gram. When I multiply that, obviously that's pretty easy math as well. That's going to be 22,590 joules of energy. Again, I'm allowed 3 digits, so that's only going to be good to the hundreds place. And let me do one more. I'm going to put this over on the other side here. We'll do number 5 over here. And again, I'm going to now heat. I've turned this water, I've turned it from here it was water at the boiling point. I've now turned it to steam at the boiling point at 100. So now I need to heat it up, and that's going to be Q is equal to M delta T Cp. And again, my mass is still 10.0. My temperature change, I'm going to 150. So 150 minus 100, of course, is 50. And that's degrees. This is grams. And times the specific heat. And the specific heat of steam, you'll see listed over here, is 1.841. 1.841. And that is joules per gram degrees C. So when you multiply all those, I got 920.5. And again, I'm allowed 3 digits because of these folks here. So this would be good to the ones place. So to get the total energy required, I have to add up 523, 3340, 4,184, 22,590, and 920.5. And when I add all those numbers up, I on my calculator got 31,557.5 joules of energy. When you add or subtract, you go by decimal place. So what I'm going to do then is say this is the ones place, tens place, hundreds place. I'm sorry. Tens place, this is the hundreds place, and then this would be good to the ones place. So I'm going to round this to the nearest hundred. So that would be 31,000, and again, that's going to round to 600 joules, or if you prefer, 31.6 kilojoules. Okay, and that is how you would determine the heat required to work your way up a phase change diagram.